Electric Machines, Section 1, Fundamentals of Electric Machines Operation. This presentation was done by Professor Joseph Guevara. The objectives of this section are to understand the basic principles of force production in electromechanical energy conversion systems, to identify the common working principles of every device used for electromechanical energy conversion, to understand how generators and motors work, and finally to identify the different type of electric machines. Before we move on, we need to answer a simple question. What is the human need of electrical machines? Well, if we think about our homes and we think about our TVs, our washing machines, our AC, our laptops or computers, our printers, our microwave ovens, we are thinking about electrical machines. So in our own homes, we have a bunch of these appliances right here that have or are electrical machines. Also, we generate electricity through these devices. Our industry depends on them. So since the mid 19th century, we have been making and developing these kind of machines, electrical machines. So in this section of our course, we're going to learn the importance of these machines and how they work. First of all, we have to state how the energy conversion process is done by an electrical machine. And this process is basically the same. It doesn't matter. It is independent of which electrical machines we are talking about. So here we have electrical energy. So we begin with having electrical energy, and then this becomes mechanical energy, or the other way around. We begin having mechanical energy, and this is transformed into electrical energy. So electrical energy cannot become mechanical energy by itself. It needs a process. So there goes the electrical machines, the motors or generators right here. So if we have electrical energy and we make this energy into mechanical energy, we're talking about a motor. But the other way around, if we have mechanical energy and we want it to become electrical energy, then we need a generator. So as I stated before, if we want electrical energy to become mechanical energy, this cannot be done by itself. We need something else. So I am presenting here the electromechanical energy conversion principle. So in order to convert electrical energy into mechanical energy, I need something called a coupling field. So this is a coupling field. We know this can go the other way around. That's why we have a double-ended arrow right here, because we can make or convert mechanical energy into electrical energy, right? So we need a coupling field. So basically, the functions of this coupling field is to store energy. So one of the functions is energy storing, and also to react to the system. This is the second function that a coupling field have. So a coupling field can be achieved by having an electric field. This can be done by capacitors, but also it can be done or achieved by having a magnetic field. There is a difference between these two, and the difference relies in that electric field stores less energy than magnetic field. That's why that's why we have to use magnetic field in order to convert electrical energy into mechanical energy, or vice versa. So this is why we have to start here, because that's what we're going to use as a coupling field mechanism. So basically, there are two types of excitation of magnetic field. The first one is a single excited magnetic system, which is a relay or a reluctance motor. We're going to talk about it later. And we also have a doubly excited magnetic system, which is basically a disenchant motor or a synchronous motor. So we're going to talk about these two type of magnetic system later on in the next section of the course. So we have to follow a simple principle, and the principle is the conservation of energy. For example, for motors, we have electrical energy input from a source equals mechanical energy output plus an increase in stored energy in the coupling field plus energy losses. We know there are gonna be some losses. Some of them we're gonna neglect them. Some of them we're not gonna even care about. But some of them are important to us, and we're gonna calculate it later on in the course. And in the case of generators, we have mechanical energy input from a source, and this equals electrical energy output plus increase in stored energy in coupling field plus energy losses. So it's basically the same. We have the same principle. In motors, we have the electrical input, the electrical energy input, and for the generator, we have a mechanical energy input. That's the difference, right? If we speak in terms of energy losses, we have that electrical energy input from source minus resistance loss equals mechanical energy output plus friction and windage loss plus increase in stored energy in coupling field plus core loss. So, for example, electrical energy here, electrical energy losses, they are in the form of heating due to current flowing in the winding of energy converter. This is called loss in the resistance. The field loss is the core loss due to changing magnetic field in the magnetic core. And windage and friction loss is due to the motion of the moving component. So here we have the loss in the form of friction and windage as, as a result of the motion of the moving components. So we can also see it this way. We have electrical energy, we have a coupling field, and we have mechanical energy. We know the process can go back, can go vice versa. So it can go from mechanical to electrical. So we have electrical energy and we have electrical loss. This is called resistance loss. Then we have coupling field, and here we have field loss that is in the form of heating. All three of these are in the form of heating, and this is from the change in the magnetic field. And last, we have mechanical loss, which is due to friction and windage loss. So we have loss in the form of heating, and they have different names. So for electrical, it is called resistance. For mechanical, it is called friction and windage loss. And for coupling field, it is called core loss. So this is another way to see the electromechanical conversion system. Is basically the same. Is basically the same equation that we have in the last sheet. So we have electrical energy input from source, and this is called WE. We have mechanical energy output, and it's called WM. We have stored energy in coupling field, which is called WF. And finally, we have energy losses, which are called W. It can be called WL or W loss, like we have it right here. So we have energy input, electrical energy input equals mechanical energy input plus stored energy in coupling field plus energy losses. So here we go. We have the same equation as we had right here. So there are basically three types of electrical machines. The first one that we've talked about is the generator, which converts mechanical energy into electrical energy. We have the motor, which converts electrical energy into mechanical energy. And last, we have a transformer. The transformer is a kind of electrical machine, but it does not have moving parts. Generators and motors have moving parts. We're going to talk about the parts later, but transformers don't have moving parts, but they have a way to convert and to change the voltage level. So they change the voltage level, so that's why they call an electrical machine, because they convert energy. There's another way to see this. We have a classification of electrical machines. So we have electrical machines over here, and there are three types, as I already stated. We have the transformer, the motor, and the generator. So for the motor, we have AC motor and DC motor. So this is the alternating current motor and direct current motor. We have the generator over here, and it's both AC or DC. And for both of them, for both the AC motor and the AC generator, we have an induction type, which are also called asynchronous motors, and we have synchronous motors over here. So for both of them, we have the same kind. So we know the principle is the same for both of these. They convert electrical energy into mechanical. This is the motor, and the generator convert the mechanical energy into electrical energy. So we know this is the coupling field. This is where we have the coupling field over here. So this is basically a classification of electrical machines, and the whole course is going to be about these three types of machines basically. So there are basically two main parts of an electric machine. First, we have a rotor. This is a rotor right here. It is the moving part of the machine. Its rotation is due to the interaction between the windings and magnetic fields, which produces a torque around the rotor axis. So this is the rotor axis. Right here, this one is a massive rotor. It is from a Dampf-Hoover motor over here. So we have this huge rotor right here. So it basically produces a torque around the axis. This is the axis right here. So it is the moving part of the machine. We're talking about either a motor or a generator, right? And the second main part is the stator, which is the stationary part of a motor, of an electrical machine. So this is the stator. It is basically static. It does not move, and the energy flows through a stator to or from the rotating component of the system. And the rotating component of the system is the rotor. So energy flows to or from the rotor into the stator. In an electric motor, the stator provides a rotating magnetic field that drives the rotating armature. So the stator provides the magnetic field that drives the rotor. In a generator, the stator converts the rotating magnetic field into electric current. So take a look of these stators right here. Get familiar with the part because we're going to talk about it a lot during the course. And we also going to talk about the constructive part of each motor as we talk about them individually. So don't worry about it. We're going to learn more about the constructive part of this. So now that we know the principles or the foundations of how electric machines work, we need to take a look at what we learned in a previous course called electromagnetism or electricity and magnetism, and review all of these previous concepts. So you have the assignment to go back to your notes or look on the internet about electric charge, electric current, what are these two and how they relate to each other. Also, we we need to know what an electric field is, how it works, We need to do the basic calculations also. And we need to know about the magnetic field, what produces a magnetic field, how it relates to electricity and electric field. So these are basically the most important. Although I don't have it here, inductance is also a very important concept. So I'm asking you to go back to your notes, and I will be uploading small videos about each and every one of these concepts. I'm not gonna be doing a lot of calculations, but I'm gonna be uploading during the next few days small videos about each and every one of these important concepts. Thank you for your time. I hope this lesson was useful to you, and I hope to see you soon.